Okay, it's just a shorthand. I know it looks like f of x notation from Math 111. It is not. I promise you, not that at all. So when you see p of x, the way you read this is it's the probability of event x happening. Did I read those okay? I'm a little bit gun shy about my handwriting today. I apologize. So when you see p of x, well, all it means is what's the chance of witnessing event x? So we look down there. I see 16.4% for p of x. What that means is what's the chance of observing a 1? X. Remember what x is? X is the random variable. X is the random variable of getting 1 pip on the die. So the chance of seeing that is about 16.4% empirically. Is that fair? Empirically? That's fair. What's the chance of seeing a 2 on the die? Empirically, 16.4%, because that's what we saw. Nobody in here is saying we should put a margin of error on that. We should, shouldn't we? Of course we should. But don't worry about that. We got to talk about how to make probabilities, how to make margins of error around probabilities. It's not as easy as a standard deviation, unfortunately, anymore. We'll come back to that, I promise. We'll come back to that. So 15.3% for 3, 16.8% for 4, and so forth and so on. Riley?
Why aren't we talking about the margin of error? Because you counted wrong anyway, so that's already an error.
Damn!
But it's plus.
Damn! Now, what you actually have just talked about, Riley, did you hear what Riley said? Because I love it, by the way. We're now talking about 2 different kinds of error. Sampling error and non-sampling error. Me counting wrong is a non-sampling error. I screwed up. That data point should be thrown away and recalculated. Theoretically speaking, in an experiment. Non-sampling error. Sampling error, however, is how you deal with uncertainty between the results you got and the actual results that exist in the population. So, what you just described, Riley, thank you for this, by the way, loved it, is the difference between empirical p of x's, which are gotten from experimentation, and because they're gotten from experimentation, Riley, thank you again, they must have a margin of error. They must. So when you read a Gallup poll, which many of you used Gallup on your exam, I was so proud of you guys. I think I graded 80 Math 243 exams, and 79 of you got perfect scores on that question number 2. The one you guys were complaining and pissing and moaning about so much. You guys crushed it. I think the only reason somebody got it wrong was they forgot to do the analysis. They gave me a graph with no analysis. I'm like, well, it's a pretty graph. I don't know why it doesn't mislead. You guys use such good terms. You said, oh, look, the scaling of the bar is this is twice as big as this, and the number's twice as big as this, so that's not misleading. Here. You did a great job with that. Many of you used Gallup and you said, look, the margin of error is right here. The graph shows the margin. Oh, happy dance. So it has to have a margin of error attached to it. Okay? Now, that's an empirical. There are also theoretical.
Shouldn't that be?
What did I say?
A2.
Or B. Sorry, I'm getting so excited. A theoretical is perfect probabilities.
Why is everything close?
Because it's very limited when you can get these. Well, there is, but it's very, very limited. These are extraordinarily limited. We can, for example, the experiment you guys just did, I very, very carefully selected the experiments we're doing in class today and Wednesday. Because the first few examples we're actually going to do the first few we're actually going to do, have perfect probabilities that I want to compare with the theoretical ones. For example, what is the theoretical probability of rolling a 1